Alright, so we're tackling our next question, which is squares of a sorted array. And I'm going to read the question. Given an integer array nums sorted in non-decreasing order, return an array of the squares of each number sorted in non-decreasing order. So first of all, let's look at what the question is talking about. Let's try to understand the question. We are given an integer array nums, so we know that we are going to get an integer array nums for our function that is sorted in non-decreasing order. This is another way of saying increasing order, but the elements can repeat. For example, you can have an array like 1, 2, 3, 4. It is increasing. This is increasing order, but non-decreasing order, that means it is in increasing order, but some of the elements can be duplicates. You can have 2 3s, 9 3s, 2 2s. So some of the elements will be duplicated or might be duplicated, but it is generally in ascending order. Okay, so and we want to return an array of the squares of each number sorted in non-decreasing order. So we want to return this array in ascending order. So if we take -4, -1, 0, 3, 10, we want to return it in such a manner that we can have 0, 1, 9, 16, and 100. So what we can do here is we want to return the squares of each number that is sorted. Now, one way to do that, or the brute force way to do that, is to just take these numbers, then we square them. We go through them with a for loop, we square them, and after squaring, we sort them. So let's do that for let me do that here, so we can say that. Okay, so we can square them in place. So for I, or for num in nums, we can say that. Okay, for num in nums, we can say that we can say, let's use an index so that we place it. For I in range len of nums. Okay, for I in range len of nums, we can say that nums I equals nums I squared. So we square it. Now this will square all the elements in it, in the array nums, and right after that we can sort it. So we can say return sorted, so sorted of nums. So let's run this and see. Okay, so this is accepted, and let's submit it. So it runs, and it has a runtime of 80.26%. It beats 80.26%, and it also has beats, so it is fairly fast. So we can see that what we did is we squared each number here. So we squared each number. We took 4 squared it, we got 16. We took 1, -1 squared it, we got 1. 0 squared it, we got 0. 3 squared it, we got 9. 10 squared it, we got 100. So this is what we did. After that, we use Python's inbuilt sorted function. Then we sorted it. We sorted it, and we got 0, 1, 9, 16, and 100. So this is a fairly good solution, but there is a better solution, in the sense that what is the time complexity? The time complexity for this algorithm is, if you look here, this is O of n squared, this is O of n, and the sorting is O of n log n. So the time complexity, overall time complexity, is going to be O of n log n. This is the time complexity. So the question is, can we do better? Yes, we can do better, and that is what we are going to do right now. So first, let me clean all this. We can do better, and the method that we are going to use to improve the speed of this algorithm is the method of 2 pointers. So first of all, we want to return an array that is sorted. So we can create an array called answer. So we can say that, okay, we have an array called answer. Now we can create the array to be the same size as the original array. So because at the end of the day, if we finish sorting everything, we are going to get the same size. So here we have 1 2 3 4 5. So we have to have 5 spots in the array. So 1 2 3 4 5. We have to have 5 spots in the array. So we have to create an array of the same size and initialize it by any number that we want. We can initialize it by 0. So let's say 0 0 0 0 0. So let's come here and say 0 0 0, but we are not going to write the zeros. Let's leave it like this. So then we'll say, once that we have this, what do we want to do? We want to square and sort everything, but this time we want to do it in one pass, in an O of n, so that by the time that we finish, by the time that we go through the entire array, we've not only squared everything, we've sorted. Remember that in the beginning we square it, after that when we come and sort it. That makes it very expensive. We use O of n log n time to do that. But this time we want to go through the array, but by the time we finish the array, not only have we squared all the elements, we've sorted it at the same time. So to do that, we have to set 2 pointers. We have to set a left pointer in the beginning and a right pointer at the end. Now this is the groundbreaking intuition. Look at both of these elements. Now the elements, because the array is already sorted, we know that the negative elements, we will have the elements at the starting are going to be smaller, and the elements at the end are also going to be bigger. So if we have 0 in the middle, then the negative 4, when you square it, is going to give us 16. But when you square the 3 here, it's going to give us 9. You see, so we cannot just say, okay, square it and put it here, square it and put it here. But if, let's say, we didn't have any negative numbers and it was just this array, we have the array starting from 0, 3, 10. The array is sorted, but it started from it starts from 0 or natural numbers or whole numbers. Then we can just say, okay, square 0, you get 0, square 3, you get 9, square 10, you get 100. But here is the case that the array that we are given, we have negative numbers in it. Now because we have negative numbers in it, we have to be very careful. We have to think, we have to look at the properties of these sorted numbers and use them to solve this question. So this negative 4, if you square it, you're going to get 16. If you square this 10, you're going to get 100. If you square this negative 1, you're going to get 1. But if you square this 3, you're going to get 9. So let me write them for you to see. Square 4, you're going to get 16. Square 10, you're going to get 100. Square negative 1, you're going to get 1. Square 3, you're going to get 9. If you look at this closely, you'll see that the numbers at the end, the numbers that are outside, when you square them, they are bigger than the numbers that are inside. So, and that is because negative numbers, when you square them, they'll turn into positive numbers. And when they turn into positive numbers, negative 4 squared and 4 squared is the same as 16. So the numbers outside, when you square them, they end up becoming bigger than the numbers inside. So we are going to use this to our advantage. We are going to use this to our advantage. What we are going to do, now that we've set the pointers to the end, is we have to take the absolute value of the ending numbers. So we take the absolute value of 4. So we can say that we have another let's take this as left number. So let's say we have something called left num. We use it to take the absolute value of the numbers at the left. So let's take the absolute value of negative 4, and we will also do the same thing. Let's do the same thing. Let's do the same thing here. So sorry, let's do the same thing here, but for the right now. So for the sake of, okay, let me just write this. So we take the absolute value of the number at the left, then we take the absolute value of the number at right. So 4 and 10, which one is bigger? So the absolute value of -4 is 4, and the absolute value of 10 is 10. Now the one which is bigger is going to yield the bigger square. You get it? So when you square 4, we are going to get 16, but when we square 10, we are going to get 100. Now the one which is bigger, we compare 116, which is bigger. 100 is bigger than 16, so we insert 100 here. When we insert 100 here, then what we do is we then we take this and we shift it over to the next element. We shift it over to the next element, so we decrement the right pointer by 1. Then we do the same thing. We compare the absolute value of 3 and absolute value of -4. So the absolute value of -4 is still 4, right? And the absolute value of this time 3. Absolute value of 3 is going to give us 3. Which one is bigger? So the absolute value of 4, which is 16, is bigger. So this time we use 4. We use the square of 16. We put it here. So you see the outer numbers, when we square the outer numbers, then we arrange them from the end to the beginning. We arrange them in descending order in order to achieve the ascending order that we want. So this 3, when you square it, is going to give us 9. So when we insert the square of 4 here, we are done with the number -4. So we have to move the pointer by 1. We basically increment it by 1. So now we have to compare. These are the new outer numbers. Because they are sorted, their squares will be bigger than the numbers that are inside, which in this case is 0. So we compare -1, and we already have 3 here. So -1 and 3, the absolute value of -1, let me clean this. The absolute value of -1 will be 1, and a square is going to be 1. So we compare, okay, absolute value of -1 and absolute value of 3, which one is bigger? Absolute value of 3 is bigger, so it is 9. So we put that 9 here. When we put that 9 here, then we move this pointer, we move it over to this place. Now we can compare this and this. So that is what we do. We look at the numbers with the absolute value, then we compare them, then we keep on moving inside using the 2 pointers approach. So when we continue this, the absolute value of -1 is 1, absolute value of 0 is 0. So we take 1, we square it, we get 1, and it's now only left with 0. So we just put 0 here. That is what we've just done. So let's look at one more test case before continuing. Now there's another test case. So first, what do we do? We build an array. So we build an array of the same size. This is 1, 2, 3, 4, 5. So we build an array of size 5 and initialize it with any random number that we want. So we initialize it with 0. So 0, 0, 0 up to 5 times, so that the length of the array is equal to 5. We have 1, 2, 3, 4, 5. Then what we do is we compare the absolute value of this and this. This will become 7, this will become 11. So this is definitely bigger than 11, is definitely bigger than 7. So we square 11, we get 1, 2, 1. Then we move our pointer to this 3, and now our pointer is still on -7. We compare -7 and 3. This will turn into 7, this will turn into 3. Then we compare 7 and 3. 7 is bigger, so we square 7, we get 49. So we put it here. Then we move our pointer, our left pointer, to this 3. We move it to this 3. We compare -3 and 3. So at this point, both of them will turn into 3. So we can put anyone we want. We can just put this 3 here and square it. Then we get 9. Then we move our pointer, we reduce it by 1. We compare absolute value of -3 is 3, absolute value of 2 is 2. So 3 and 2, 3 is bigger than 2. So we put the square of this one here, 9. Then now both pointers are pointing to the same number. Both are pointing to the same number, that is 2. So we put the square of this one here. So this is sorted 4, 9, 9, 49, 1, 2, 1. So let's look at how to write this in code. So to write this in code, first let's refresh this and see. First of all, we have to get the length of the array. We are going to use it in the code. So the length of our original array is length of nums. We store it. Then we are going to create another array which is our answer. Then we initialize that array by 0 to hold the places for the numbers that we are going to arrange, and its size is going to be n. It's going to be basically the same size as the original array that we had. Then in the original array, we are going to have a left pointer and a right pointer. The left pointer will point to the first element, and the right pointer will point to the last element. Notice that the last element is indexed in n-1. So what do we do? So now we take our time. Let's observe something and see. We are going to iterate through the array, through this array n times, right? We are going to iterate through the original array nums. But as we iterate through the original array, we are going to iterate through it n times, and we are going to store it here. We are going to store it each time. We are going to store it here. So what we normally do for arrays is we can just start from, okay, for I in range, let's say n, in range n. You see, that means if n is, let's say 5, then that means you are going to start from 0, 1, 2, 3, 4, 5. But we can also count n times by starting from the end. For I in range, so we start from the last element. So we start from 5, you get it? And we go up until the last element here, which is 0. So because of Python's one of feature, we put -1, and anytime we'll just be reducing by 1. So when we find the square, for example, we found 1, 2, 1 first, we put it in the position of 4, index 4. We put it in index 4. We start with index 4. We put it in index 4, then we reduce it, then we find the next one, we put it in index 3, we put index 2, index 2, index 1, then index 0, then we run it n times. So we can also run this n times by starting from the end and basically putting these numbers at the end of our answer array. So we say for I in range, we start from the last element, we go to up until the first element in the array answer, and we decrement it by 1. So this for loop is for when for us putting the answers in the array answer. So we come, then we check. Now basically we have the left array, right? Now the left array is going to have a left number. So the left array is basically going to turn into absolute value of the nums of left, and the right array is going to turn into a right number, which is the absolute value of the nums of right. Okay, so now we have the absolute value of the left number and the absolute value of the right number stored in left num and right num. So what we have to do is we have to compare. Now if the absolute value of the right number is greater than the absolute value of the left num, then what we know for a fact that we can store that number at the end of this array. We know that that number will be the biggest number in the entire, will have the biggest square in the entire array, in the sense that whenever the outer numbers are big, so the outer number at the left and the outer number at the right, the one which is bigger is going to have the biggest square. So in this case 11 is bigger than 7. Because the absolute value of 11 is bigger than the absolute value of 7, we can just store 1 to 1, but we have to store that 1 to 1 at the end. That is why we are iterating through the array from the end. We are iterating from the end of this array answer and inserting the answer from the last position to the first position. So the element at index 4 at the last index will be equal to the right num square. So we square it and put it there. Then we have to reduce the right pointer by 1. If this is not the case, then that means it is less than or equal to. Now if it is less than, then we are going to say that okay, the answer of the last element will be equal to the left num squared. Then we increment the left pointer by 1. So after doing this, then what we have to do is we have to return answer. So we have to return answer, and in this case, let's run this and see. So it's passed the first 2 test cases, and it has also passed this one. So let's look at the time complexity and space complexity. The time complexity for this algorithm is O of n, because we basically only go through the entire array n times. And the space complexity, now this is a tricky one. The space complexity, the answer asks us to return an array, right? To return an array. So that means that no matter what we do, we have to create this array. So that array is part of the question requirement. So our array or our space complexity is O of 1. We cannot write this algorithm without returning anything, and we are not doing it in place either, because it is literally impossible. So at least in my knowledge, it is literally impossible. So we have to return O of 1. So we return we have to return a particular array, because the question requires us to return an array, or the question requires us to basically have a data structure. We cannot do it without a data structure. We create an array because it is part of the demands of the question. We basically count it as the space complexity is O of 1. We did not create any additional unwanted space. If we created an additional array or additional hash map or any other data structure that the question specifically did not require, then in that place we use extra help. But in this case, the help that we are using is the help that is specified by the question. It is basically needed. Without it, we cannot solve the question. So we cannot solve the question in O of n time. So we created this. We created a necessary hash map. So our space complexity is O of 1. So far, this is the best algorithm that I can think of, and I hope it helps me to revise in the future and helps anyone who watches.